In this video, we're going to learn about two other periodic trends. We're going to learn about electronegativity, and we're going to learn about electron affinity. Previously, we learned about atomic radius and the trends observed with that property on the periodic table, and we learned about ionization energy and how it was the opposite. Ionization energy being how much energy it takes to remove an electron from a neutral gaseous atom. Atomic radius being basically related to how big the atom is. So the bigger the atom is, the easier it is to remove an electron. And we actually just saw that with the calcium, magnesium, and aluminum reactivity demo. Now, electronegativity is how strongly an atom attracts electrons in a bond. And this has huge implications in the world, because when you have two atoms coming together to bond, they don't necessarily share the electrons evenly. Sometimes they do, sometimes they don't. When they don't share them evenly, what we end up with is polar bonds, and that leads to, if the geometry is okay with it, it leads to polar molecules, which completely determines whether or not something will dissolve in water, which basically leads to all molecular organization in the world. Pretty important stuff, actually. And moving forward past this class, definitely the most important concept to remember out of this class when you go into organic chemistry or anything like that. So, it is, however, linked to ionization energy, because both of these trends have to do with how strongly electrons are attracted to the nucleus. And they're both inversely related to how big the atom is. For example, fluorine can't help herself, she's so attractive. And that's because fluorine is relatively small. You notice that the noble gases don't exist in this, because this has to do with electrons shared in a bond, and since noble gases don't bond, that's kind of a moot point. So, again, larger elements are down here. They have low electronegativities. They don't compete that strongly for electrons. And smaller elements, which exist at the upper right of the periodic table, which we went into why that happens in the previous episode, are very good at attracting electrons. So if you have a bond that occurs between a metal, which is relatively weak with respect to electronegativity, bonding with a highly electronegative element, you will end up with an ionic bond, or a stealing of electrons. When you have two things that bond together that are somewhat different, you end up with a polar bond. If you have two things that are very close in strength, you end up with a nonpolar bond, which again leads to solubility. Now, just to visually picture this, if we have two elements and one's big and one's small, the smaller element's nucleus is going to be closer to the electrons being competed over than the larger element's nucleus. So this will have a greater force of attraction observed relative to the other atom, and therefore it's able to pull the electrons towards it. Yep, that went twice. Electron affinity is the energy change observed with the addition of an electron to a neutral gaseous atom. So when you have a negative energy change, that means it's going to become something more stable. And that means it's energetically favorable. A negative value is a good thing in this case, because it means it's more likely to happen. When we look at the elements, and you can see the general trend is that like fluorine has the highest value. Again, similar to electronegativity and ionization energy, it's going to be very good at attracting electrons due to its size. However, there are a couple exceptions that exist, or things that break the trend in this picture you can see here. One is you can see that right here you have values greater than 0. Values greater than 0 are not energetically favorable. And what we need to look at to kind of discover why that's occurring is the electron configuration. If we look at beryllium, for example, which has 4 electrons in a neutral atom, to add one more electron to that, you're going to have to put it in the 2p subshell, which is higher in energy. And we learned from the Aufbau principle when we were writing electron configurations, it requires an addition of energy to get an electron to go into a higher energy state. So to go from here to here, quite a bit of energy. You also have an exception to the trend when you look at nitrogen. You can see that that's greater than 0. The reason for that is you're now going from having a nice 1 electron in each of the orbitals, and now you're having a paired one, which has increased repulsion, making it less stable, requiring more energy to put it there. The other obvious one is the entire column of noble gases. Noble gases all have complete electron configurations, complete S&P subshells. So to add an additional electron, you would have to put it into a higher energy level. Again, energetically not favorable. So that explains the breaks in the trend that you see here. It all has to do with how the electrons are arranged. But the general rule The smaller the atom, the more strongly it's going to hold on to electrons, the better it's going to compete for electrons. The larger the atom, the less able it is to compete for the electrons, and the easier it is for them to lose it.